All right, so we're going to talk about heat this week. And the first question we're going to ask is, what is heat? All right. Let me just make a note of the fact that there is going to be an extra credit lab opportunity. I'm going to mention that when we get to it in the book, right? But that's the only thing that may not have been on your schedule that I handed out at the beginning of this semester. All right, so what is heat? So that was a question that men debated, right, to try to determine, really surrounding this question here: is heat matter or not? What does it have? What does something have to be in order to be defined as matter? What did we say were the two things required?
Take up space.
Take up space, and does anybody know the other one?
Have mass.
Have mass, right? So, man, there were a bunch of answers there. Cruz got one. I saw Lily. And then I heard someone else saying it over here. It's hard to tell with the mask on. Who else said has mask?
We kind of all said it.
Y'all kind of all said it together? Wow, you're making a pitch for multiple, like this whole group here. I might as well give it to the whole class, right? All right, let's see. So we got Joey and Jerry and was Caden? Were you in on that one too?
I'm silent, so don't count.
Okay.
Yeah.
All right. So we'll start there and we'll see what else happens. So it has to take up space. Who said that one?
Cruise, right?
Cruz has to have mass and has to take up space, right? So does heat qualify as that? So that was one of the topics that they debated. And so back in the 1700s, they said, yeah, it's matter. And we're actually going to give it a name, and we're going to call it, they said it was a gas, and they called it caloric. It's from the Latin word for heat, which is C-A-L-O-R, calor. I may be saying that completely wrong, but anyway, it comes from that Latin word. So that's what was commonly accepted as the case for heat, that it was a gas, it was matter. And so when you felt that sensation of heat, then that was actually a gas that you were feeling. But James Prescott Joule kind of changed all that. He challenged that theory in the mid-1800s. And he showed experimentally that energy produced heat, and thus if heat was matter, energy could be destroyed to create matter. And he was like, that's kind of pushing what I believe to be true concerning God. His Christian faith wouldn't let him accept the fact that we created matter. He said that's God's business. And so he basically is the one that we credit with coming up with this idea that heat is in fact energy. It's not matter. It's energy, and that's why we use common unit for energy is the joule, named after James Prescott Joule. Okay. So let me give you a couple of definitions here, and we're going to the beginning of the class is just going to be basically defining some terms for you. So what is energy? Energy is the ability to do work. Robert, do we have a Robert in here? I don't think we do, because I don't want to pick on anybody in the room. Robert, clean your room. I just don't have the energy, I don't have the energy to do that, right? It's the ability to do work. So that's what energy is. But let's define technically what work is, all right? So energy is the ability to do work, but what is work? Well, work is the application of a force to move an object over a distance. So Robert, go clean your room. I don't care if you don't have the energy. Okay. So Robert goes to clean his room, and he sits there, and he goes to pick up something from the floor, and for 2 hours he stands there like this. Is he actually doing any work? No, because he's got to actually move whatever that object is that needs to get picked up, right? So it's a force that's applied. I can push against the wall here, but if the wall doesn't move, then I'm not actually doing any work. You've got to move it over a distance, all right? So that's our definition for energy and work. From a chemical standpoint, this should kind of make sense as we talk about heat, because if heat is energy, then we know that when we apply heat to substances like water, for example, what happens? All of a sudden you get all this movement, right? So as we add heat to a system, as we add that energy to a system, the molecules will begin to move faster, the atoms will begin to move faster. And so that concept should sort of make sense to us. Now, when we talk about heat, we always want to talk about temperature, right? That those kind of go hand in hand, but they're not the same thing. And you may say, well, obviously, they're not the same thing. Heat is at a certain temperature, but it's surprising how whenever we kind of start looking at some of the equations dealing with these topics, how students will make the mistake of thinking of temperature and heat as the same thing, and they're not. So they're related, but they're not the same thing. So heat is energy that is exchanged because of a difference in temperature. So it is related to temperature, or a difference in temperature, or a change in phase. So if there's a change in temperature, the energy involved in that, we refer to that as heat, or when a substance changes from one phase to another, that energy we call heat.
What if it gets colder?
There's still an energy exchange there. If it gets colder, it gave up energy, it lost energy. So we're still talking about heat in both cases, and you'll see that when we start. It's a good question. As we start doing some of our formulas, sometimes what we're calculating will have a negative sign, and that means we lost energy. If it's got a positive sign, we gained energy. So that's a good question. I wish you would have asked it just a little bit later, because it's been a great segue. We're not quite there yet, but it's a good thought. We need to hold on to that. All right, so before we start talking about those things, though, I want to define a calorie. This is an energy term that we're familiar with, but this is not the calorie that most of us think of when we think of calorie. Okay, this is calorie with a little c, lowercase c. And this calorie here is the calorie that chemists usually use, and this is the amount of heat required to raise 1 gram of water (1 degree Celsius). That's how we define little c calorie. The amount of heat required to raise 1 gram of water 1 degree Celsius. The food calorie, which is what we're more familiar with, what we generally think of when we say a calorie, that's a capital C. And I'll give you a conversion relationship here. You need to make sure you know this. 1 calorie. So that's how do I write that down? This is calorie for food. So that's an uppercase C. 1 calorie, the food calorie is equal to 1,000 chemistry calories, okay? All right, so just to kind of have a frame of reference, when we talk about the food calorie, you know, an average diet would be around 2,000 calories, right? Give or take, depending on your size and how active you are, or how much you eat, right? May have nothing to do with activity; it just may have to do with your appetite. But 2,000 calorie diet is enough energy to raise 5 gallons of water 100 degrees Celsius. So that's pretty impressive, right? The energy that you consume in food in one day is enough to raise the temperature 100 degrees of 5 gallons of water. Pretty impressive. So you could take that water all the way from freezing to a boiling point, right, with the energy contained in that. You don't have to memorize this, but I wanted to make you aware of it. And if you need it, I'll give it to you on a test. But just so you can kind of correlate the two, 1 chemistry calorie is equal to 4.184 joules. All right, so no need to memorize that. I will give it to you, but just so you know the relationship there. All right, any questions about that? All right, so let's talk about something that's called specific heat capacity, and this is where we'll start. You know, we're always working towards there being some sort of mathematical problem that we do. So, specific heat capacity, what is that? Specific heat capacity is the amount of heat to raise a specific mass of a substance 1 degree Celsius. Often this is just called specific heat. The term capacity there won't be included. Often this is just called heat. So I want you to see the chart. Page 392 for values. I will give you that chart or the specific heat value on a test, bless you, if you need that. But where's my book? There it is. There is one substance that I want you to memorize the specific heat for, and that is liquid water. You'll notice as you look at the chart, at the table, page 392, that water is listed on there in 2 phases, in solid form and in liquid form. So in liquid form, and that's the only one that's bolded on the table, is water. So the let's see. So memorize specific heat capacity of liquid water is, this number is going to look familiar, 4.184 joules grams degree C. It's the same, because you didn't have to memorize this, but I do want you to memorize this, all right? And that kind of makes sense to us, right? Because we defined calorie as being related to raising a substance 1 degree, 1 gram of water, 1 degree Celsius, right? So it makes sense that those numbers would be the same. The higher the specific heat, the harder it is to heat up that substance or cool it down. And so is water easier to heat up and cool down in its liquid form or solid form? Huh?
Is it solid?
It's easier in the solid, right? Because it's got a lower number. So the higher the number, the harder it is to do that, to heat it up or cool it down. The experiment that I was talking about, this is related to specific heat. So experiment 13.1 on page 391. You can do that experiment home if you want to. Really simple, and you just need like a candle and a balloon, 2 balloons, a water sink, nothing major there. So that's a really easy one for you guys to perform at home for extra credit. All right. I will say there are some of you looking at the grades going at the point that we are. We're getting closer and closer to the end of the year, and some of those grades are dipping a little bit to the lower side, so I would highly recommend taking advantage of that extra credit if you're one of those individuals, so that bombing a test near the end of the semester doesn't put you in really bad shape, okay? All right, so let's see. Make sure you memorize the one for water. Any questions about specific heat capacity? We're gonna give you a formula now and do a problem, do a couple of problems related to that. So the formula that I want to give you is related to measuring heat, and it uses this specific heat value. So that's why we had to introduce that term. So I'm gonna put this over here, measuring heat. Not measuring temperature, but measuring heat. Heat is defined as Q equals M times C times change in T. All right? And where Q is your heat, so this variable represents energy, since heat is energy. M, as you would expect, represents mass. This C right here represents specific heat, or specific heat capacity, right? So those values on the chart, that's what C refers to there. And then change in T is the change in temperature, and change in T, you can just think of that as this, the final temperature minus the initial temperature. All right? So you'll notice if the larger mass gets, the bigger this number here, then the bigger this number here, right? So the more of a substance that you have, the more energy it's going to take to heat it up and cool it down. All right, let's do a problem. Page number 394, example 13.1. We've got a couple here. And it says a 500-gram block of copper starts out at 51.2 degrees Celsius and cools to a room temperature of 25 degrees Celsius. How much heat did it lose? All right, so when we're speaking of copper here, we're going to use our equation Q equals M times C times change in T. It's asking for how much heat did it use. So we're trying to find this value, how much heat did it lose. We're trying to find this value Q here. They give us C. It's probably on our chart there too. Yeah, copper's listed in the middle of the chart there. It's 0.386 joules per grams degrees Celsius. Got kind of a weird unit there. It's kind of like R in our PV equals nRT. You know, that had a really bizarre unit. So what's our mass? The mass that's given is 500 grams. The C that they give us is 0.386. Like I said, if we're not talking about water, I will give you the C for substance if you need it. So they gave it to us in this problem here. And it started out at 51.2 degrees Celsius and it cooled to 25 degrees Celsius. So let's figure out change in T. So we can plug that in. So change in T is going to be the final temperature it cooled to room temperature, so the final temperature was 25 degrees Celsius, and it started out, minus the initial temperature, it started out at 51.2 degrees Celsius. So this temperature is going to have a negative value of 26.2 degrees Celsius. So that's what we're going to plug in right here. Negative 26.2 degrees Celsius. So notice you got to make sure that you do this, take the difference of those two values in the correct order, right? So that you end up with either a positive or a negative value as it's appropriate. If it cools down, it should make sense to you that the temperature change is going to be negative, right? Because the overall temperature decreased. So when we plug that in, we get a value of negative 5,060 joules. So that's the energy, that's the heat that was lost whenever this 500 gram block of copper cooled down. And the reason it's negative here is because it was heat that was lost. It was energy that was lost. Okay, if it had warmed up and gained energy, we would have had a positive value there. So that's our final answer. Any questions about that? Everybody clear on what I was talking about with the sign, making sure that you get the negative versus the positive sign. Make sure you put these temperatures in the correct order when you're calculating and changing T. Okay? All right, let's do one more. This one says we have a 350 gram iron horseshoe. So that's our mass. Mass equals 350 grams. It's the substance is iron. And they give us the value for C, for iron, they say is 0.44 joules per grams degrees C. By the way, let me make this quick note, just backing up to the previous problem. If they had given us this value in something like kilograms, the mass had been given in kilograms, what would we have to do? Why do we have to convert it to grams?
Because
that's the unit.
Because the specific heat, right, that has a specific unit. And the grams aren't going to cancel out if these don't match up, right? If we had left this value in kilograms, we'd have had some kind of bizarre unit that had kilograms and grams in it, along with the joules, and it would not have been correct. So you need to make sure that for example, if you were given temperatures in Fahrenheit, this thing here, this can't change, right? These are given to us in the table, so it's got degrees C, so we'd have to convert degrees Fahrenheit to degrees C. So make sure that your units all match whenever you're writing those down. That's one of the good things about writing the units in the actual problem, so that you can identify any issues like that. All right, so we got a 350 gram iron horseshoe. A blacksmith adds 59 kilojoules of energy to it. All right, so Q is given as 59 kilojoules. If the horseshoe started out at a temperature of 22 degrees Celsius, we're given an initial temperature of 22 degrees Celsius. What is the final temperature? So in this particular problem, we're trying to find TF, final temperature. All right, so what's the first thing that you would recommend doing here? Rearranging the equation. That's a great idea. So here's our equation, and we want to solve for what?
T or TFF.
TFF. So we're gonna just solve for change in T right now, and then we'll take that value and plug it in here and rearrange that as necessary. Okay. So let's just rearrange this guy to solve for change in T. So just to kind of go through the algebra one more time, because I still see people making mistakes with this. If we want to get change in T all by itself, then we want to divide by M, and it's M times C. So we're going to do that on both sides. So that way these guys will cancel out. All right, so change in T then is going to be equal to Q over M times C. All right? That's the equation that we're going to use to figure out the change in temperature. Sometimes if you start plugging numbers in this, you can get confused because you stick units in there and all that kind of stuff. And so to me, it's kind of easier to rearrange that algebraically if you leave it as the variables. All right, so we've got that. Anything else we're going to have to do before we start plugging in numbers?
You have to change kilojoules to joules.
This has to be in joules, right? Because our C value is in joules, not in kilojoules. So I'm just going to write that down below here. If this is kilojoules, then the joules value for that would be 59000. Right? You could write that out. 59 kilojoules times joules on top. 1,000 joules is equal to 1 kilojoule. And so that'll give you 59,000 to do that. 59,000 joules. That's what we got to put in our equation. All right, so let's plug those values in. 59,000 joules over, the mass is 350 grams. That unit's fine. Times C, which is 0.444 joules over grams degrees C. So we plug that in our calculator, and we get 380 degrees C. Is that our answer? That is not our answer. Why not? Huh? No, that's not the reason why.
Because that's the change in the temperature.
That's the
It's
change
not
in
the
T. We're trying to find TF, right? So we're going to use this other equation for that. Change in T equals TF minus TI. So we're going to rearrange that for TF, right? So that means that TF is equal to change in T plus TI. And so now we're going to plug in our values, 380 degrees Celsius plus TI was given to us as 22 degrees Celsius. And so when we add that up, we get 402 degrees Celsius. All right? They went to a little more trouble in the book.
It was negative 22 degrees Celsius, I think. Was it?
You rearrange and that made it.
I was just.
Yeah. Because it would have been negative here when I plugged it in, but because we brought that to this side of the equation, it became positive. But yeah, the initial value was 22 degrees. They didn't say that it was negative 22 degrees. Don't be confused. The book says 4 times 10 to the second power degrees Celsius. They're just trying to maintain the significant figures. That's why they did it like that. I told you guys I'm not as concerned about you sweating over significant figures at this point. I'll accept that answer. All right, any questions about using the equation for specific heat or measuring heat and using the specific heat capacity in that equation?
Do you think they would ever give us, would they give us the mass in moles and then we have to convert it into the
I mean, they could, right? That's one of the, since that's stuff that we do all the time, that's absolutely something that you might be expected to remember from previous chapters, because that doesn't go away. Like just about every test, it seems like we're converting from moles to grams or vice versa, right? So that would be a great way to sort of mix things up and give you something like that. I don't remember that being the case, but it's possible. So,
ideas.
yeah, I appreciate that. I'm making a note right now. Change this test problem to include the number of moles. I don't see a problem like that, so I don't think you're going to get asked that. But you should. That's like straightforward and easy, right? I mean, if we said instead of 350 grams, which metal was this?
Iron.
This was iron for this last one, 350 grams of iron. And if I said we have whatever number of moles, right? You're just going to take the number of moles and you're going to look up the grams of iron. You're going to say, you're going to look up the AMU and you're going to say this many grams is equal to 1 mole. I mean, that's like a super simple calculation. And if you're still struggling with this, we got a bigger problem, right? This is something that we need to talk about after class, because this is stuff that we've been doing, should be doing in our sleep at this point. So yeah, that would still be very easy. All right, so let's go to where do we want to talk about now? We just talked about specific heat capacity. Like I said, if Q is negative, then it lost energy. If it's positive, then it gained energy. So our last topic we want to talk about today, and we'll be done, is calorimetry.
That's exactly what I was thinking.
It's like stoichiometry.
You guys didn't talk, you haven't used that word in a sentence this past week? Calorimetry? Really?
Yeah.
Wow. We say that all the time at my house. Not.
To add that to the vocabulary.
Right. So calorimetry. Calorimetry has to do with using a device that we refer to as a calorimeter. So what is a calorimeter? It's a calorimeter is used to measure specific heat capacities. All right. So it's just a device that we use. We use a thermometer to measure temperature. We use a thermometer. We use a calorimeter to measure specific heat. All right. And we told you about the Latin word, right, for heat being calor. So heat. It's a heat meter, right? Specific heat meter, calorimeter. So you see a picture of one on page 395. And you notice as you look at this device, you've got an object that sits inside the liquid, right? That sits in the bottom of the container there. It's immersed in this liquid. The liquid is usually water. But the object is hotter. Notice that it's labeled it as a hot object, right? So the object is hotter than the liquid that's in there. And you have this thermometer that's basically measuring the change in the temperature of the liquid as the object begins to cool down, and it measures the temperature change up to the point to where the temperatures are the same, right? So you stick this hot object in there, you let it cool down, and eventually when it cools down, what's going to happen? Everything in the system is going to be the same temperature eventually, right? So if it's hotter than the water or whatever liquid's in there, the liquid's going to heat up, right? It's going to be warmer than it was, and the object's going to cool down so that at some point they're going to be the same temperature. So you're measuring that in a calorimeter to determine the specific heat. And so we use this equation with calorimeters. We say that a negative Q for the object, that hot object in there, is equal to the Q of the liquid plus the Q of the calorimeter. Now sometimes this guy you hear, the calorimeter, heat is negligible, often negligible. It's small enough compared to everything else that you can ignore it. So you may, if it's often negligible, so you may be able to ignore. And I'll tell you the problem if you can ignore it or not, right? To ignore. So we're going to do a problem in just a second that uses that equation, but there's an important note here, and you're going to see why it's important whenever we do this problem. An important note, and that is in a calorimetry experiment, the temp of the liquid and the calorimeter are always the same. All right? So if we have to take the Q of the calorimeter into account, and I say the liquid starts at this temperature and it heats up to this temperature, that means the calorimeter did exactly the same thing. Started at the same temperature, heated up to the same temperature. Okay? In addition, the final temp of the liquid liquid, the calorimeter, and that object object that was hot when it went in and the object are all the same. So if you know T final for any of the items in this calorimetry experiment, you know T final for all of these items, right? You know it for the object, the liquid, and the calorimeter. And so we'll do an experiment, not an experiment, we'll do an example that kind of shows you why that's important to recognize that. All right, so any questions, though, about this definition or this note here? And this is where the difference between heat and temperature are important, because I had one student, when they read this in the last class, they said, oh, so you could really rewrite this as negative Q of object equals, if these are then identical, so you could say negative Q of object equals 2Q. I said, no. Q represents the heat. Q represents the energy. The energy is not the same of the liquid and the calorimeter, just the temperature, right? The energy equation has change in T in it. So change in T will be the same when you calculate Q for these, but the Q will not be the same. Because remember, the Q has to do with the mass, how much water's in there, the mass of the calorimeter. It has to do with the, also has to do with the the C, right? The specific heat capacity of the liquid that's used and of the whatever materials in the calorimeter. So don't make the mistake of thinking that these values are going to be the same. There would be no point in even writing an equation like that if those values were the same, right? But the temperature change is going to be the same for those guys. All right, let's do example 13.2. And that example says a 45.9 gram sample. I'm going to erase this so we have room. So, 45.9 gram sample of an unknown metal is heated to 89.7 degrees Celsius. So the object, the hot object that we put inside of our calorimeter, we don't know what it's made of. All right? It's an unknown metal. So, but what we do know is that the mass of this object, the mass of the object equals 45.9 grams, right? It's heated to 89.7 degrees, and then it's dropped into a calorimeter that contains 150 grams of water. So what is that 89.7 degrees Celsius temperature? In all of our equations that we've had today, what would you identify that temperature as? The initial temperature of what? Of the object. So the object's TI is 89.7. All right? All right. So that's important that you make sure you know which TI you're talking about, right? It's dropped into a calorimeter that contains 150 grams of water. So in this case, water is the liquid that we're using in our experiment. So the mass of the water is 150 grams. The initial temperature of the water is 25 degrees Celsius. So for the liquid, the initial temperature is 25 degrees Celsius. And then by the end of the experiment, the temperature increased to 26.9 degrees. So the liquid final temperature is 26.9 degrees Celsius. What is the specific heat of the metal? So we're doing all of this to try and calculate C for the object, right? That's what we're trying to figure out. So let's see if we have enough information here to do this problem. We want to find the specific heat of the object. They say ignore the heat absorbed by the calorimeter. That's the last statement, right, that's made. So what that means is that this part of our equation goes away. We don't care about that because that's negligible. We don't have to worry about it. So we're just working with the fact that the Q of the object, negative Q object is equal to the Q of the liquid. Well, we're not given either of those values, but we can calculate. We have enough information to calculate one of them. Which one do we have enough information to calculate? What do we need in order to determine Q? We need to know the mass of the object, we need to know the specific heat of that object, and we need to know what the temperature change is for that object. So do we have all that information for the object or for the liquid?
Also the liquid.
We have all of it
And
for
there's
the
water,
liquid.
so we know this.
We know because we've memorized, right, what the value is for water. Because we know that C for water, we memorized that is 4.184 joules per grams degrees Celsius, right? So we can figure out Q of the liquid. So let's go ahead and do that. Q of the liquid equals mass. The mass of our liquid is 150 grams times C, and we know that that's 4.184 joules over grams degrees Celsius, times change in T. We'll write change in T up here. Change in T for water, for the water or the liquid, is the T final of the liquid, which is 26.9 degrees Celsius, minus T initial, right? T final minus T initial, which is 25 degrees Celsius. So the change in T for the water is 1.9 degrees Celsius. So that's what we put here, 1.9 degrees Celsius. Is everybody following me so far? So we put that in to our calculator and we come up with a value of 1200 joules. So the Q for the liquid is 1200 joules. Well, per this equation, we know that negative Q for the object is equal to 1200 joules. It's equal to whatever the Q for the liquid is. So that means Q for the object then is equal to negative 1200 joules. Does everybody see that? Algebraically, you can just think of that as multiplied -1 times both sides, or divided -1, both sides by -1, or whatever. All right, so now we've got Q for our object. We've got the mass for our object. We're trying to find the C for our object. Do we have change in T, or can we calculate change in T for our object? We're given the initial temperature of our object. But do we know the final temperature of the object? It's always the same, right? If we know the final temperature for anything in these calorimetry experiments, we know the final temperature for everything, right? Because it all ends up being the final temperature in the end. So that means then that change in T for the object is going to be equal to the final temperature, which was the same as the final temperature of the liquid, 26.9 degrees Celsius, minus the initial temperature of our object, which was 89.7 degrees Celsius. So that value is negative 62.8 degrees Celsius. Negative 62.8 degrees Celsius. All right, so we're trying to find C, and we've got all these other values, so we should be able to do that now. So the only thing I want to do real quick is just rearrange this equation to solve for C. So if Q equals MC change in T, then that means that C, we're going to divide this side by M and change in T, just like we're going to divide this side by that. Whenever you do to one side, you do the other. So that will cancel out with that, and we get that C is equal to Q. That's a terrible Q. C is equal to Q over M times change in T. And so in this case, Q for our object is negative 1200 joules. M for our object is right here, 45.9 grams. And the change in T for our object, we calculated that to be negative 62.8 degrees Celsius. So punch that in our calculator and we get 0.42 joules per grams degrees C. And that's what all of the values on our specific heat table, they have that unit there. So we know that our unit worked out right. We have all the right values in our units. Also, if you look at the specific heat capacity table, you'll notice that all the values are positive. And so we would have been concerned if this had turned out to have a negative value. And that's why when we got a negative value here for Q object, it should have made sense to us that the change in the temperature was going to end up being negative. So those negatives would cancel out. We get a final positive value. All right. So I'm just curious. It's not? All right. I was wondering if we could have identified what metal it probably was, but we can't. We can see it's close to
Right in between zinc and nickel.
zinc and nickel. Yeah, okay. Maybe it was a metal made of zinc and nickel, right? It's combined, maybe so. We'll assume that. All right, any questions? That's all I have today. So we're done unless you got another question. All right.